Right, we just saw Bayes' rule, yeah? And remember that the whole purpose of a classification problem is to find the distribution of the label giving the data, yeah? Because then we can predict the label. Now what is Bayes doing? Bayes is actually allowing to solve the other problem. Yeah, we can swap these. Yeah? So we can also look for what is the probability for me to look at the data once the label is given. Yeah? So given the label, what is the data? Yeah? So that's an important item. Another way for us to derive Py conditional on D would be to approximate P by looking at the data. Maybe if we look at the data, we can find the parameters of the distribution. Yeah? So we do that based on an example. Your data set is a coin toss, and we do 10 tosses. Yeah? 10 coin tosses. And this is the result. Head, 2 times tail, 3 times head, 4 times tail. What we're gonna do is a maximum likelihood estimation. So MLE is a maximum likelihood estimation. And what we're gonna do is we're gonna try to find the parameters theta of the distribution that would make it most likely that I would observe the data D. Yeah. Now let's see what that would be. Remember, in a coin toss, it's 50-50. We flip 50% head, 50% tail. We can associate this with the Bernoulli distribution. Don't worry, we'll look at Bernoulli in just a moment. But you have a Bernoulli distribution. Bernoulli. And it has a parameter P. Yeah? And what is the parameter P? Well, the chance that x equals 1 equals P. And the chance that x equals 0 equals 1 minus P, because the sum needs to be 1. So let's call the chance that we have heads. Yeah? So let's call x is 1 heads and x is 0 tails. So let's look at heads. So the probability that we get heads now equals, we have 10 coin tosses, so the denominator will be 10. How many times we face head? 1, 2, 3, 4. 4 times head. So that's 40%. Of course, 40% is not very accurate, because we know it's 50%. So that's one of the issues with the MLE, is that the result may not be accurate, especially when the number of times you do the experiment is limited. In this case, 10 times. Yeah, it's actually not a lot. We should do a lot more experiments in order to get closer to where we need to be. So it's definitely not something that you would do when there's a small amount of coin tosses. Another danger you see, of course, is here. Yeah, in this case we have 4 times tail in a row. Imagine you start your experiment here and you get this, then the chance of heads is 0. Yeah? So what people usually do is they add a few numbers there. We call this smoothing. Yeah? For example, they can add 1 to the 4 and they can add 2 in the denominator. Yeah? So this is a type of smoothing that you would need to do. Okay? So that's one option. The other thing we can do is called maximize a posterior. And what happens in maximize the posterior? Well, people consider theta as a random variable. Remember, in this case, we consider theta as a parameter. In Bernoulli, that was a parameter p, is basically your theta. But here, theta is a random variable, and a random variable has a distribution. The distribution is p of theta. And this distribution we call the prior. The prior distribution means that you have a gut feel or some knowledge that the distribution of theta or the parameter will be p, and that p is 50% for a coin toss. And then when you know p of theta, then you can use base the probability distribution of theta given the data set equals probability of theta times the probability of B is dA, d given theta, divided by the probability of d. So this allows you to calculate the distribution of theta given d from the base rule. This is base. So this is the prior, as we have seen. And probability of d given theta, this is actually your MLE. Okay? So that's the second way on how to find the distribution or the parameters of the distribution.